So, welcome to my dear students and learner. This is the today we are going to discuss already in the previous lecture. I have given you the brief idea about prompt and delayed neutron, and also we have seen in the beginning the fissile fuel consumption in a nuclear reactor and how it is to be calculated, and once it is loaded, how long this will be that will be able to produce the rated power output that we calculated. Typical calculation I have shown. So for any kind of nuclear reactor, fission reactor, you can, if you understand that concept, you can able to do by your own. Also, we have discussed there the prompt neutron. So basically, prompt neutrons are those neutrons which released just after the fission occurred, and uh, which have very high kinetic energy, and the population of the prompt neutron is uh, the majority of the neutron population inside the reactor will be the prompt neutron, and very small fraction of neutrons which are coming comparatively slower rate from the delayed neutron precursors. Those are called delayed neutron, but those neutron uh, is very important to control the reactor. So today we will, with the help of uh, mathematics, we will understand how this delay. I told that without the in the last lecture, if you remember, that only if in a nuclear reactor, only if only the prompt neutron exists, then the controlling will be much more difficult, because the prompt neutron will be releasing within a nanosecond or picosecond range just after the fission occurred. It's very fast, but the effective multiplication factor, uh, it will be basically maintained by absorbing such neutrons by the movement of the absorber rod. And those are this absorber rod drive mechanism. Those are a electromechanical system which have much more higher time constant. So it is very difficult, and I have shown one typical example that if a nuclear reactor is only populated with prompt neutron, and due to some transient condition, if the effective multiplication factor slightly increased, then within a fraction of second the neutron population will be increasing in an uncontrollable way, and this will be a very difficult condition. So as we will introduce one new term here, which is beta, or delayed neutron fraction. It is very simple to understand that the delayed neutron by total number of neutrons inside the reactor, which are prompt neutrons and the delayed neutrons. Okay. So using now, if you see the previous derivation, there I only considered all the neutrons inside the reactor which is generating from the fission. Those are prompt neutron, and using considering that assumption, we have calculated the instantaneous neutron population. Now we will modify those equation slightly, and we will try to understand pictorially also, and at the end of the lecture I will plot the instantaneous curve for the neutron population or the neutron population growth in case of only prompt neutron, and the neutron population growth when the effect of delayed neutron is considered. And with these two things we will understand how once the delayed neutron produced, then the reactor control become much more easier, and it is more or less, it will be always in um, steady state. You can see that transient effect will be very, very less. Here this is we will do little bit mathematics, because rather than speaking uh, with the literature and the theory, if slightly if you work out with mathematics, it will be much more clear. So already we are familiar with the this first equation. So this is basically, it is from the Fick's law and the diffusion equation. So this is the thing here. This term I have introduced, one term is called beta, that is the delayed neutron fraction. Okay, even though it is very less in case of uranium 235 fission, the neutron which will be coming out, that will be around 2.45 per fission, whereas the prompt neutron will be 0.0065 per fission. It's a typical figure. You can refer the textbook, and those equations are taken from the standard textbook. You can follow. And I have introduced one more term called rho, which is reactivity. That is basically K infinite, that K effective minus 1 divided by K effective. This one term I have introduced. Okay, this is basically rho. And now here this lambda. What is this lambda? Basically this lambda, it is the that decay rate for the, there will be conventionally the fission fragment will go for a beta decay, but as I told in the previous lecture, that some of the fission fragment, some of the neutron enriched fission fragment, that can go for neutron decay. Okay, so and after that only it will be stable. So this is the that neutron decay factor, and C is the concentration of that delayed neutron uh, precursors. Okay, and this is the continuity equation for the delayed neutron precursors. This both the things I am writing from the standard textbook and based on the Fick's law and diffusion equation. So these are, we need to, and here one thing you have to remember, that for the for a particular composition of fuel mix, there will be several uh, neutron enriched isotopes, or there will be different groups of delayed neutron precursors, and you have to consider all these things. You can take you can see the typical examples. There will be somewhere it will be 6 groups, somewhere it will be 8 groups. So for calculation simplicity, I have taken all these things together, because if you take, say there is a 6 groups of delayed neutron precursors. So if you write these 6 equations. So to solve this sets of differential equation, it will be empirically it will be quite difficult. So for the simplicity, I have coupled all the groups together and consider that variable as C in case of this is a concentration of delayed neutron precursor for all possible groups, and this lambda is the average decay factor for all the delayed neutron precursors. Okay, so these are the 2 equations you can refer. That's why I'm telling if you want to know detail about this, you can refer any standard book and you can find it out. Now I am going for the solution, and I'll go fast, very fast about this. Here is a little bit mathematics, but you don't worry, it is very simple. So in nature, if you want to do generally, it is difficult to solve sets of differential equation through standard method. So either you have to go for infinite series solution, or here we are what we considered, we assume 2 solution. For the first equation, the solution is like this: the instantaneous neutron, it will be some constant into e to the power omega t. Omega is the frequency. Okay, and for this delayed neutron precursor concentration is equal to some another constant into e to the power omega t. Okay, now if you put this value, if you put this value value of n here and substitute, if you differentiate this, so it will come like this, these 2 equation. Simply we are in place of n we are putting a omega t, and here in case of C we are putting b omega t, and if you differentiate, the left hand side will be differentiating of this, and right hand side it will be as it is like this. Okay, now you can see here this omega t, every from here this omega t e to the power omega t is cancelled out from everywhere. And now if you write that things, if you take all the things in the left hand side and write in a matrix form, it will come like this. Okay, now to get a non-trivial solution, means say it's a non-zero solution, say one equation x square minus x, that is equal to 0. So here one solution is x is equal to 0, is satisfying this equation. We are not considering this kind of solution. X is equal to 1 also one solution, non-zero solution. So for the non-zero solution of the above the earlier sets of equation, means this sets of equation, so what you need, what is the necessary condition? That the determinant should be 0. So determinant means this into this minus this into this, so it is like this. And now you can see this, finally this equation, it is becoming a quadratic equation of omega. So now you know this it is minus b plus minus root over b square minus 4ac by 2a. As you know, this lambda, here we will go for some some more assumptions. So this lambda is a very small, this constant is a very small negligible value. Okay, so definitely where the lambda is multiplied with some quantity, even though this this diffusion time, that is also in the order of maybe millisecond or microsecond. So compared to this beta minus rho, this LP lambda, it will be much more smaller. And similarly, this beta minus rho plus LP lambda, that quantity much more higher than this quantity, LP rho lambda, because LP also a small quantity and lambda also is a small quantity. So this assumption, this is a fair approximation, we will consider this fair approximation, and we will what we will do, we will try to approximate the two roots which are omega 1 and omega 2, and it will become like this. And now if you consider the solution, as we started this exercise is as n is equal to a e to the power omega t, and now we obtained that there are two solution, omega 1 and omega 2. So now that n I can modify that equation, instantaneous equation of n, as a1 omega 1 t e to the power omega 1 t and plus a2 e to the power omega 2 t. And similarly for that delayed neutron precursors concentration also can be written in this form. Okay. Now we will and here one more thing you should remember, that this, as I told, this lambda is a smaller quantity. So as it is multiplied, so the amplitude of omega 1, it will be much more lesser than the amplitude of omega 2. Okay. Now we will take from this two differential equation, we will consider the boundary conditions, where at t is equal to 0, there are at t is equal to 0, system is in steady state. Okay. So that time all the means no reaction started, fission not started. So that time this dn dt also 0 and dc dt also 0, and the at t is equal to 0, your k effective is equal to 1. So I have considered that I have written the reactivity is equal to k infinity minus 1 by k infinity. So your rho also, it will be as at the beginning your system reactor is in critical condition, so your reactivity will be 0. Okay. And your initial neutron concentration, that is equal to also this considered I written as n0. Okay. And similarly for this equation also, it is converted like this. Okay. And now already we found that instantaneous solution of this is n is equal to a1 e to the power omega t1, and if I put t is equal to 0, so this equation is converted to this, and this equation is converted to this. Okay. And now in the second equation, and from here these two equation, you see these two equation is more or less same. More or less, these two equations are same only. So here we can that value of C0 we can find out in terms of N0. So C0 is equal to your C0 is equal to beta N0 by LP lambda. C0 is equal to beta N0 divided by LP lambda. Okay, LP lambda. So now in this equation, in the second equation, you can put C is equal to your B B e to the power omega B. So that I am putting here and getting this equation. But you remember now the omega having two roots. One is omega 1 and omega 2. So this if you put that, so here so basically now this side it will cancel out, this will also cancel out, and this will also cancel out. So your A will be basically in the next things I have written here. Basically from this equation, if you find out A, so your A will be, you take your this B omega plus lambda B divided by this term. So that's why I have written B1 is equal to this into A1 and B2 is equal to this into A2. and already we have obtained the value of omega 1 is this one and omega 2 is this one. So if you substitute, so b1 and a1 relationship we will get, and already I told c0, we from the initial condition we obtained this value, and if you substitute this b1 and b2 value here, it will come like this. Okay, and already we know that n0 is a1 plus a2, and now for calculation for substituting one term, I am multiplying all the terms by beta minus rho. Now this term will cancel out and you will get the value of a1, and similar way you can get the value of a2 also. Okay, so by doing this exercise, finally I got the n by n0 is this one. So basically this value is omega 1 and this value is omega 2, as I told, compared to, because in this omega 1, why that lambda is multiplied. So lambda is a small quantity, so if it is multiplied, so this term is this exponential, this term is very negligible, very small one term. So compared to this it is negligible, so this term we will cancel out, the first term we will cancel out, and we will leave only, we will keep this term. Okay, so now in a final conclusion, this already you are familiarized. If we consider in a nuclear reactor only populated by from neutron, then the instantaneous neutron population equation, it is like this. Okay, and considering the delayed neutron, what we did in this lecture, we have understood that your n by n0, that is equal to this, and this term is your omega 1, and already we have with some approximation we have understood that the value of omega 1, it will be the amplitude of omega 1 is much more lesser than the amplitude of omega 2. So this entire, this term can be cancelled out, and what is left out is this term. From this two equation, now we will try to plot this two equation and we will try to understand what is happening. So for that I have written a very simple code. You can see for a particular situation, I have considered that now the reactor is running um, in a critical condition. Okay, it's a prompt critical. So say it is the effective multiplication factor, due to some reason, it is in from 1 it is increased to 0.00655. It's a typical figure, and for uranium 235 the delayed neutron fraction is 0.0065, and I am plotting these two equations, whatever the at last we, so we will be plotting this x e to the power k infinity minus 1 by lp into t, and minus rho by beta minus rho into e to the power minus beta minus rho by lpt. These two equation we will plot, because the second one, the first one we have not considered the effect of delayed neutron, but in the second equation we have included the effect of delayed neutron, and we got the solution. Okay, so see here I am plotting the both the function from 0 to 1.5 second. I have defined this value a, that is minus rho by beta minus rho, which is this one, the coefficient. Okay, and then the diffusion time I have considered arbitrarily taken as 1 millisecond, and the tau, which I have taken this tau means this term, this minus beta minus rho by LP. So that's a, you see, minus beta minus rho by LP. And this Y, basically this is the instantaneous neutron multiplication factor in case of when we considered the effect of delayed neutron. And this Z function, this is basically the instantaneous neutron multiplication factor when uh, delayed neutrons are not considered. We considered all the neutrons as inside the reactor are from neutron. Now if we are plotting these two functions, you see here the green line, sorry, the blue line, this is more or less stable when the it is around 882, and after 6 it is some 891. But you see after 1 second, that means 1.35 second, suddenly if it is only from neutron, the equation, the neutron population, it is started to increase exponentially. So there, that time, so fraction of seconds, within few, not within few seconds, the neutron population will multiply like anything. So that time, how you will move the absorber rod to control the situation, and this transient handling, it will be much more difficult. So that's why I told in the beginning of the discussion that prom neutron, we should thankful to prom neutron that prom neutron is there inside the reactor. That's why we very nicely we can control the neutron population, hence the fission, and we can control the power of the reactor. So this is all about today's discussion. Hope I could able to give the deliver the idea why delayed neutrons, even though the fraction of the delayed neutrons are so less, but still how it is significant and so much important to control the reactor power to handle the transients. Thank you so much. Thanks for your patience. Hope you have learned something.